Okay. All right, this is going to be a continuation of our discussion in section 8.1, where we're going to continue talking about integration techniques. For example, let's look at this one. Find the integral of 1 over the quantity x squared minus 4x plus 9 dx. Well, in this particular case, there's not much that you can do with it in its current form. So what I need to do is be creative and be manipulative. And since we've been talking about these three new formulas, the integral of du over the square root of a squared minus u squared, the integral of du over a squared plus u squared, and the integral of du over u times the square root of u squared minus a squared, it would follow that we're going to be looking at these particular types of integration techniques. And so what I want to do is look at this particular problem up here and notice that there are no square roots in it. So that's going to preclude the first and the third formula, which means that I want to try to put this thing in the form of du over a squared plus u squared. Well, I can do that by taking the dx here and moving it here, and then hoping that I can come up with some sort of u substitution. But when I look at this part right here, this trinomial is not factorable. But I should notice that this right here is the beginning part of a perfect square trinomial, such as x squared minus 4x plus 4. If I had this particular trinomial, I would then be able to factor it into x minus 2 quantity squared. Well, where am I going to get this from? Well, one of the things that we need to notice is this plus 9 here is the same thing as plus 4 plus 5, which means that I now have x minus 2 quantity squared plus 5 as my new denominator. And so I can go ahead and rewrite this integral so that it looks like this. And that's the manipulation that I'm talking about. I look at these things and I try to find a way to make it fit over here. Like I said, the first and the third are going to be out of bounds because of the square root symbol, but I can definitely make this fit like this. Remember that I got an a squared plus u squared. So what I can do is go ahead and rewrite this. So that's the integral of dx over x minus 2 quantity squared plus, make that 5 plus x minus 2 quantity squared. And now you'll note that this is looking more like this formula right here. I've got the dx in the numerator, and I've got this a squared plus u squared. Now, obviously, that 5 is problematic, so what I can do is rewrite it as the square root of 5 quantity squared. Once again, I haven't changed the value, it's still equal to 5, but now I have a squared symbol here, which means that this inside the parentheses will be my a. And I then have the x minus 2 quantity squared, and that means that this right here is u. And so I'm going to use this formula right here, and I know that a is equal to the square root of 5, and u is equal to x minus 2. So therefore, this is going to be equal to 1 over, and this is a, and remember that it's the square root of 5, times the arctan or tangent inverse, u over a. Well, remember that u is this right here. So that'll be x minus 2, and that's going to be over a, which in this case is the square root of 5. And then don't forget that we have a plus c. And yes, I can go ahead and rationalize this if I want, but this will be sufficient for this particular problem. I will go however, and put brackets around this to make sure that we know that the arctan is being evaluated for x minus 2 over the square root of 5. Now, that brings us to a problem like this, which at this point, we don't have any sort of technique. And in fact, a lot of times what would happen is I could go ahead and rewrite this simply as x minus 1 to the negative 1 power, and this would be an integral, over the radical, which is the square root of 4x squared minus 8x plus 3, and then still have the dx. And then I could try a u substitution. Let's let this be u, and that's equal to 4x squared minus 8x plus 3. The problem comes when I try to take du here, which is going to give me 8x minus 8 dx. I do not have an 8x minus 8 anywhere in this, but I do see an x minus 1, so let's go ahead and rewrite this as du equals 8 times x minus 1 dx, and therefore 1 over 8 times du is equal to x minus 1 dx. But I don't have this anywhere. This is not this. They are not the same. So I need to try something else. This does not work. So the next thing that I might try is to take this and distribute it over these two values. So that means I now have 1 over the following, which is going to be x times the square root of 4x squared minus 8x plus 3 minus 1 times the square root of 4x squared minus 8x plus 3, and that would be dx. And if I look at this, I can go ahead and convert this into the square root of x squared. That way the x squared can multiply all three of these terms under the radical, and this becomes the integral of 1 over the square root of 4x to the 4th minus 8x cubed plus 3. That would be 3x minus the radical 4x squared minus 8x plus 3. The problem here is there's nowhere to go. Okay, I could try a u substitution, and we could simply say that u is equal to 4x to the 4th minus 8x cubed, and that should be a square, plus 3x squared. Therefore du will be equal to 16x cubed, and I can already see my dilemma, minus 24x squared plus 6x. I do not have, and that would be a dx, I do not have the 16x cubed minus 24x squared plus 64 anywhere in my integration, so this also is a dead end. So what to do? Well, once again, let's get creative in how we approach this. I'm going to rewrite the integral. Remember, it's the integral of 1 over the quantity x minus 1 times the square root of 4x squared minus 8x plus 3 dx. Now, as I said, we want to do some manipulation. So let's examine this thing right here, because this is what's problematic. Now, I'm thinking in terms of doing something similar to what I did in the last problem, and that's because I want to be able to factor this thing. And I note that plus 3 can be rewritten as plus 4 minus 1. Now, why would I care? Well, I care because this right here is 4x squared minus 8x, and that doesn't change, but I can factor a 4 out of all 4 of these terms, leaving me with 4 times x squared minus 2x plus 1 minus this 1 on the outside. Now notice that the x squared minus 2x plus 1 is a perfect square trinomial, and I can go ahead and factor it into x minus 1 quantity squared multiplied by 4, and I subtract 1 from both sides. And now you'll notice that this right here is the same as this right here. And the reason that I'm looking at that is because we are going to be considering the following form, which is going to be du over u times the square root of u squared minus a squared. And if we take the integral of that, that's simply going to be equal to 1 over a times the arcsecant of the absolute value of u over a plus c. Now, I'm not quite done, because this right here is my squared part, and I have this u squared, but I have this problem of the 4 out here. And remember, this whole thing is still underneath the radical symbol, okay? But I notice that I can rewrite this as 2 times x minus 1 quantity squared. And then I have the minus 1 here, and that'll still be underneath the radical. And I get that because 4 is simply 2 squared times x minus 1 squared is going to give me this under here. Now, this is going to become my u. U will be equal to 2 times x minus 1, okay, which I can rewrite as 2x minus 2 at some point if I want to. And I also note that a is going to be simply 1, because this right here is my a squared, therefore a is equal to 1. But I'm not quite to the point where I can do something, because this right here is not the same as this right here. Well, like I said, we're using manipulation, so what I'm going to do is I'm going to go ahead and multiply this by 2. And that becomes 2 times x minus 1, and I now have a u. However, if I do that in the denominator, I'm going to have to do it in the numerator, because I can't change the value, I can only change the way it looks. So now I look at this and I say, okay, I'm going to bring this 2 here out in front, and I now have 2 times the integral of dx over 2 times x minus 1 times the square root of 2 times x minus 1 squared minus 1 squared, because I want to put it in that u squared minus a squared format, And this is simply going to be equal to 1 over a. Oh, but wait, we forgot, or I forgot, that there is this 2 out here. And that's going to be important. So I can't forget that. So this will be 2 times, and then we'll have 1 over a, which in this case is 1, times the arcsecant of the absolute value of u, which is 2 times x minus 1, all over a, which in this case is 1, plus c. Now obviously that's a little messy, so we would want to neaten it up a little bit and rewrite this simply as 2 times the arcsecant, or the secant inverse, of the absolute value of 2 times x minus 1 plus c. And like I said, it's all about manipulation. You got to be thinking in terms of how can I change this so that it looks exactly like what I need it to. And you know what? I'm actually going to go ahead and continue to refine this down to the 2 times the arcsecant of the absolute value of 2x minus 2 plus c. So let's look at another one. And this one's going to involve using our friend, the arc length formula. We want to find the arc length of the graph of y equals ln of sine x from x equals pi over 4 to x equals pi over 2. So like I said, we're going to need the arc length formula, which will be equal to the integral from a to b of the square root of 1 plus f prime of x quantity squared dx. Now obviously we're going to find that as we progress through the course, these integrations are actually going to become harder and harder. So the first thing I need to do is figure out from y equals the natural log of sine x what y prime is. And you know that when you take the derivative of ln of sine x, you're going to end up with cosine of x over sine of x, which is simply equal to the cotangent of x. So now I know what f prime of x is. So in this particular case, what I'm going to do, and just in case you were wondering where this comes from, remember that in this case I would be using the formula y is equal to ln of u, and I would use the chain rule. Y prime would be equal to u prime over u, and u is sine of x in this case, and therefore du would be equal to the cosine of x. And then obviously when I take the derivative of the natural log of u, I get 1 over u. Okay, now we want to go ahead and continue by figuring out what my limits of integration are. Well, this is a and this is b. So the arc length is going to be equal to the integral from pi over 4 to pi over 2 of the square root of 1 plus, remember it's f prime of x quantity squared, so this would be the cotangent squared of x dx. Now in this case, when I go to take the derivative, or take the integral of this, I have never dealt with 1 plus the cotangent squared of x underneath the radical, but I do know that due to my trigonometric identities, this is a Pythagorean identity, and this whole thing can be rewritten as s is equal to the integral from pi over 4 to pi over 2 of the square root of the cosecant squared of x dx, and I know that the square root of the cosecant squared of x is going to be equal to the cosecant of x. So this becomes the integral from pi over 4 to pi over 2 of simply the cosecant of x dx. And in this particular case, we're going to have to remember the formula for this one, and that's going to be equal to the negative natural log of the absolute value of the cosecant of x plus the cotangent of x evaluated between pi over 4 and pi over 2. And of course, when we go to evaluate that, we will have the following: negative natural log of the absolute value of the cosecant of pi over 2 plus the cotangent of pi over 4 minus the negative natural log of the absolute value of the cosecant of pi over 4 plus the cotangent of pi over 4 . Now, since this is going to become a plus symbol between the two, we'll just go ahead and get rid of that and convert it into a plus sign. And I know when I look at this, I can rearrange this so that I have a natural log of the cosecant of pi over 4 plus the cotangent of pi over 4 minus the natural log of the absolute value of the cosecant of pi over 2 plus the cotangent of pi over 2. And I just noticed a mistake, which I'm sure most of my students will call me out on. That should have been pi over 2. Not sure why I wrote pi over 4. Okay, now that I have this, I can go ahead and start to do some evaluation, remembering that the cosecant of x is equal to 1 over the sine of x, and that the cotangent of x is equal to 1 over the tangent of x. So that means I can take the cosecant of pi over 4 and convert that into 1 over the sine of pi over 4, which will be equal to 1 over the square root of 2 over 2, or actually 1 over the square root of 2, so this is going to be equal to the square root of 2. And we can take the cotangent of pi over 4, and that's going to be equal to 1 over the tangent of pi over 4, which in this case will be equal to 1 over 1. Which is equal to 1. So let's go ahead and find the cosecant of pi over 2. And that will be equal to 1 over the sine of pi over 2, which will be equal to 1 over 1, which is 1. And then the cotangent of pi over 2 will be equal to 1 over the tangent of pi over 2. And when we look at this, we say, oh, whoa, tangent pi over 2 is undefined, and I have 1 over undefined, which is undefined. But let's go ahead and do a little bit more manipulation. We have 1 over the sine of pi over 2 over the cosine of pi over 2, which is going to be equal to the cosine of pi over 2 over the sine of pi over 2, which in this case will be equal to 0 over 1, which will be 0. So now I can go ahead and say that this is going to be equal to the natural log of the absolute value of the cosecant of pi over 4, which is the square root of 2, plus the cotangent of pi over 4, which is 1. We notice that that is a positive value. And this is going to be minus the natural log of the absolute value of the cosecant of pi over 2, which we know is 1, plus the cotangent of pi over 2, which we know is 0. Now what do I have? I have the natural log of the square root of 2 plus 1 minus the natural log of 1, which is going to be equal to the natural log of the square root of 2 plus 1 over 1, using the formulas for logarithms to condense the expression. And that's simply going to be equal to the natural log of the square root of 2 plus 1. Now that's my exact value, and I can change it and go ahead and calculate it using my calculator, and we would get 0.8814, and this is going to be in units because I was not told what the arc length units were. Now remember, at this point you have got to remember to put units, because I guarantee you by the time you get to this point you've actually forgotten what it was that you were originally trying to do. You've just been concentrating on evaluating the integral.